Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Folks at Saarbrücken started doing ray tracing just on PCs and clusters of PCs, and again demonstrating that you can actually bring this down to commodity hardware in the space of about a year. All of a sudden, it sort of became taken for granted that you can do it on commodity hardware, and since then, Tim Purcell and folks at Stanford and John Hart and Nathan Carr at Illinois have used the GPU to accelerate this. So the point is really that we're not going to talk about how do you do interactive ray tracing, that we're sort of taking it for granted that it can be done. Lots of people have shown that it can be done, and either it's just a matter of time, maybe there's some architectural embellishments that we need, but we can do it. So the question becomes, why? What do you do with ray tracing? Why would you want to do interactive ray tracing? And this is a big question. What can you do with a ray-based renderer that you can't do with a polygonal rasterizer? And of course, there's several answers to this question. We're not the only people to have a motivation section in our talk, and some of the answers that people have talked about when they sort of try to motivate why you would do ray tracing and interactive rates is one is sublinear complexity. There's a classic argument that's that the amount of time that ray tracing is really only weakly proportional to the number of polygons in your scene, because it's directly proportional to the number of pixels. And even today, we've all got a million pixels on our displays. We rarely want to display a million polygons all at the same time. So of course ray tracing has been slow, but the number of pixels is for the most part increasing slower than the number of polygons. And so this notion of sublinear complexity becomes more and more attractive as our environments get more and more complex. And that's a valid argument, but on the other hand, that kind of depends on having a good acceleration structure, which more or less means static scenes. Now, people are doing work on how do you get good acceleration structures for dynamic scenes in ray tracing. How do you get fast ray tracing on complex environments that are changing? But it's by no means a solved problem. And for that matter, if you've got a static scene, you can build a good acceleration structure. You can use occlusion culling on rasterization hardware and get pretty good speed up too. So I think the sublinear complexity argument is not the best one. Probably one of the best arguments is just that it's a much more natural framework for doing really powerful lighting and shading. Okay, so there's all these sophisticated rendering techniques that you can do very easily in ray tracing. They just kind of fall out: reflection, refraction, shadows, indirect illumination. All these techniques sort of fall out of ray-based rendering, and this is a valid reason that you would want to do this kind of rendering in an interactive setting. But you could argue that these effects, or some reasonable approximation, are increasingly possible with rasterization hardware. And so, how often do you really need real reflections as opposed to just what you get out of an environment map? Oh, can you use pre-computed radiance transfer to get some indirect effects? So while I do think this is a valid argument, it's not as strong as it could be, just because we do have very good hardware, very fast rasterization hardware, and it's getting very flexible. Speaking of flexible, another reason you might want to use ray tracing is just that it's easy to define new primitives. You can do direct ray tracing of spheres. Everybody does that in intro graphics, or NURBS, or implicit surfaces or volumes, or anything else. On the other hand, rasterization hardware, once more, is becoming increasingly programmable, and a lot of the fast ray tracers restrict themselves to triangles just for sheer speed, because they want nice, small, regular data structures that are easy to process. So the thing that, these are all valid points and good, their motivation to work on this, how do you do interactive ray tracing? But something that we've gotten excited about is the fact that in a rate-based scenario, you can vary the sampling rate. And of course, this is old news in ray tracing if you're going to vary the sampling rate across the image, right? So you might send more samples to regions where there's color contrast, or high-frequency textures. Any place where there's sort of the signal is changing across the image, you're going to send more samples, and that's been done since the early days of ray tracing. I'll just point out that in an interactive setting, actually, ray-based rendering is a pretty convenient place to do vary sampling rate according to other scenarios. So, for example, if you think you know where the user is looking, because you've got an eye tracker or a good model of attention or whatever, then you can have more samples where they're looking and fewer where they're not looking. Although you might still have to have high temporal sampling where they're not looking, because we're pretty sensitive to change out there. And this is, you might have fewer samples for things that are moving quickly across the retina, than things that are fixed. So just there are some opportunities that come out of this ability to sample with very fine granularity, to target your rendering computation with very fine granularity. But more interesting than that is the fact that you can actually, in an interactive setting, think about varying the sampling rate across time. So this is basically the idea that, hey, when the signal is changing, when the scene is changing dramatically, maybe you need to sample more frequently. Or maybe you need to sample more frequently only in those parts of the scene that are changing dramatically. So if you've got a more or less still image and something moving across it, you can devote all of your rendering resources to resolving this thing that's moving, and you don't need to constantly recompute this part of the image that's not moving. So so this fits very naturally into array-based render, and that's one of the reasons that's sort of exciting. Why is it important to be able to vary sampling rate across time? Because now you can get temporal coherence in image generation. Okay, so the there's a very loose hand-wavy argument here that look, temporal coherence is important, right? And this is, you could pick this apart, but the it's roughly true to say that there's like an order of magnitude more compression available in a video stream than in an image stream. And without trying to sound too rigorous about it, because we're not, but just broadcast quality MPEG-2, roughly 0.2 bits per pixel is what you can expect. Same quality JPEG, roughly 2 bits per pixel. So the point is that there's a lot to be gained from temporal coherence. Most interactive settings have high temporal coherence. We use this all the time in image generation, but it's very natural to use this in array-based render, where you can actually render with much more, control your rendering with much more granularity. So this is what we're doing. We're trying to rethink interactive rendering and the spatial and temporal sort of strategies that we use for sampling in interactive rendering. And then we have to deal with the problem, how do we reconstruct images out of those sample streams? So there's a lot of related work. I've just listed a few things here. There's more that could be listed. Just to briefly go through. So one thing that I mentioned that's work by us, by the same group of people, because we're going to return to it later in the evaluation section, is this interruptible rendering paper that we had last year at the Interactive 3D Symposium. So the idea of interruptible rendering is that it tries to do level of detail control that directly trades off spatial error, or an image being drawn very coarsely, to temporal error, where an image is drawn late. Okay, so the idea here is that we've got two different rendering streams. In the colored silhouettes, you see exactly what the renderer should draw. If you had sort of an ideal 100% perfect and perfectly fast renderer, then it would draw a bunny in the position of these two colored silhouettes. On the left, we've drawn a bunny that's very coarse, but it was very quick to draw this. On the right, we've drawn a nice fine detail bunny, but it took so long that it's in the wrong place on the screen. So this notion of there is temporal error caused by rendering delay. So interruptible rendering was a rendering scheme that tried to balance the spatial and temporal error directly, by actually directly comparing them. And as a crude way, you can think, for example, that maybe the temporal error is proportional to this distance here, and the spatial error is proportional to this distance here. So in some sense, the spatial error, or the image on the left, is actually more accurate than the one on the right, because it's in the right place. More work. Just-in-time pixels is the name of a system out of UNC that sort of reinvented the notion of beam racing from the early flight simulator days. I was talking to Kurt about this at lunch. The just-in-time pixels. The idea was basically what they were doing here is they were recomputing viewpoint and object positions at the beginning of every scan line instead of at the beginning of every image. And and this is important because that image is actually going to be displayed to the user over the course of many milliseconds, right? The time it actually takes you to scan something out on a CRT or any sort of raster scan device is non-zero. And so when you're drawing something down at the bottom of the image, it's taken longer than when you're drawing something at the top of the image to get there. And so they tried to account for that. So think of all of these approaches as rendering techniques that tinker with the temporal sampling, when you take your samples. Frameless rendering is the core idea that we're sort of building on, and so I'll show a little video. Frameless rendering is the idea that instead of accumulating all of our rendering results into a single frame and then only then showing that image to the user, we're going to do it sequentially. So this is a video from that Utah system that used the SGI supercomputer. And so here's a video of framed imagery, and you can see that it's really slow. This is classic double buffered rendering, and they've got a complex environment, and so they're even on their system they're achieving less than a frame a second. And here's frameless rendering. The idea is that we're going to generate the same pixels, and we're going to generate them at the same rate. But whenever we recompute a pixel, we're going to throw it up on the screen immediately, and not wait until we've got an entire image accumulated. And this is, and we're going to compute it with the latest input from the user. So the result is this, you see both the good and the bad, right? It's very low latency, very smooth motion. And if you were interacting with the system, you'd probably find it easier to interact with in many ways. But you get this kind of aggravating, scintillating noise because a lot of those pixels are stale. During moments of motion, many of the pixels on the screen are old. They're stale information. So you can think of what we're doing as sort of rethinking frameless rendering. How would we do this right? What kind of things would we do to make this better? Sample reuse. There's a whole lot of techniques out there that have tried to reuse rendering results from previous frames. We're hardly the first people to think about that. One example is the render cache by Bruce Walter and colleagues, and they've done the idea that the render cache is if you've got say a ray tracer, a fairly slow render, you can only afford to update. In this case, it was like 1/16 of the pixels in every frame. Then, here they just went through and updated 1/16 of the pixels in every frame, and you can see that the result is very blurry. On the other hand, if when you cast a ray and it goes and hits something, if you take that result and think of it as a colored 3D point, you can reproject that point to figure out where it would land on the screen as the user moves. And presumably, this is a cheaper operation than reshooting the ray to begin with. And so this notion of reprojecting samples gives, in the case of the render cache, much better results. Now they've got this nice clean image. So there's a whole lot of work that's been done in this vein, and we're just sort of picking one here. Two sort of similar pieces of work, the Talisman architecture, which started right here. Reuse chunks of the image, would render a piece of imagery and then reuse it for several frames by using affine warps, for example, to move it around as sort of a sprite. Regan and Pose also had this nice paper in 94, 92, something like that. 94, I guess it was, where basically they took distant geometry and rendered it into a frame buffer that only got updated, once or twice a second. Nearby geometry would be rendered into a frame buffer that was updated 30 times a second, and to have a couple of other frame buffers in between. So they sort of break up near-field and far-field geometry and do different temporal sampling strategies depending on how far away stuff was. And the final piece of work that's related that I'll just mention, although it's not a rendering scheme per se, is reconstruction from sparse samples. So what we're going to end up doing is we're going to be generating samples. Only some of them are valid, some of them are less valid than others. So we have to create at some point we've got to create an image for the user to see from all of these samples. And this is the reconstruction from sparse samples problem. And there's a variety of work on this. There's some nice pull-push variations on pull-push techniques. This particular one is from Daniel Kohanor's work with his students at Tel Aviv. And this is what they do is they take an image and they sample very densely along line segments and throw out. They weren't supposed to do this. And throw out most of the pixels. So you've got maybe 1% of the actual data here, and then they do their little reconstruction step and reconstruct that image, and all of a sudden you can see what it is. So we have to do something akin to this. We have to find a way to reconstruct a full image from sparse samples. Okay, and I think now I'm going to turn it over to Ben, who's going to give an overview of what we're actually doing.
Okay. So we're actually doing two components. There's two parts to this work. One is adaptive sampling, both across space and time. And basically what we're going to do is update more, sample more often in regions of spatial chain, edges of the image, but also regions of temporal chain, where things are moving around. Similarly, then what we'll do is collect all these samples into something we call a deep buffer. And this buffer is not just a frame buffer with all the samples representing the same moment of time or the same period. It has actually some temporal depth to it, so that's what we call it deep. And then we'll take those samples and we'll try to reconstruct an image from those samples. Because we're focused on interaction, we're going to try to reconstruct the most current image we can. And then in order to facilitate that, we'll be varying the shape and the volume of the footprint of the filter. So there are three parts to the system we're building. The first is the sampler. The second is this deep buffer. Again, deep, it has both spatial and temporal extent. And then we'll have this reconstructor. And the buffer and the reconstruction are being done with Dave and his student Louis at Virginia. And then I'm doing the sampling and the buffer at Northwestern with my student Abhinav Dial. So, first of all, talk about the sampler. The sampler is just like in many spatially adaptive renderers, tracks color change over space, and it uses a tiling. But it also has to track color change across time because it's interested in change. And so it uses a tiling like many other schemes do, but these tiles don't exist, they have a depth in time, so they extend into the deep buffer age. And our goal then is to bias rendering for regions of change. And the way to do this is by, instead of explicitly representing some kind of a probability distribution, what we do is we try to manage this tiling interactively so that they all have roughly equal probability, or they all capture roughly equal amounts of color change. Yes?
Like in editing, there's also this notion of motion compensation. Yeah, just not just essentially just saying throw it up your hands when things change, but saying, well, we can make a model to predict how things change, and really the cost is like how bad your prediction is, not just the fact that things change a lot, but the fact that you can't predict how things change.
Right. Well, we'll get to that. What we're going to describe now is something that samples more often where there's change, but we're not actually, in the current prototype, we're not actually doing motion compensation, but that will be like our next step. And then once we've since we're managing these tiles so that they contain roughly constant amounts of color change over space or time, to render, all we end up doing is picking one at random, and then picking a pixel or some pixels within that tile at random for rendering. So this is a peek into the sampling. What we're showing here is no fancy reconstruction. We're just showing the latest samples at each location, the most recent samples at each location in the buffer. And so you can see here that we're sort of faithfully capturing the back, the middle of this moving object in a fairly static scene with viewpoint data, but not the front very well. And we're trying here with our tiling, these colors just come in to illustrate the tiles. We're focusing our render is focusing on the front and the back of the car, because that's where those temporal edges are. So it turns out that what we've built is a pretty tight closed-loop control system. I'm not an expert in control theory, but we've talked to people, and it turns out this control system is fairly complex. So it's very high-dimensional, it's very nonlinear. The reason it's a closed control system is because we're taking the output from the ray tracer from our sampler. Instead of just putting it in a simple buffer for reconstruction, it becomes feedback for rendering files. And then we stick it into the error tracker, managing files. We ideally would like our files to have no color change in them. Probably won't reach that state. But then we bias rendering toward those regions that have the most color change, or spatial or temporal edges. Even though we can't do a nice analysis on what is a fairly complex control system, there are some engineering techniques we can apply. One thing that we get, because of this self-monitoring, because of this control system and this feedback, is we get really nice portability. So we can take this render and stick it on a new machine or use a different sampler, and the system will adapt in a quite fine manner to rendering changes in rendering platform or system. Yeah, sure.
How does the error correction work now? You can't compute what the image should be, because obviously that's what
Right.
it's so magic.
It's not magic. The assumption is the same assumption that all adaptive renderers make, which is that if there's a lot of color variability, if I'm uncertain about the color, then I'm probably not done. And in this case, unlike in a frame
Based on the sample.
yes, I just use that. And in this case, unlike a classic frame renderer, that's a moving target. Right? So the frame, we're not having a monotonic decrease in the input error because things are changing with speed. So because in addition to that portability, we have this nice proportional response, right? I've talked about sampling more where are changing over either space or time. And it also turns out to be useful to respond to the derivative of color change. If color change is increasing or decreasing, odds are we need to look at that region even more actively. And so that's called a PD controller. We also turned out to be useful to use gain control. So the basic notion here is that if the image is changing quickly, our estimates of how well we're doing are probably not as trustworthy. Right? So what we need to do is back off, reduce gain, and the way what that translates to in this context is reducing the number of tiles that we're using to bias our rendering, because we're less confident in our ability to track how well we're doing. So it might go up if things are static, the number of tiles, it might go down if things are dynamic. So here are a couple CSAT PD control and gain control. Here on the left, this is a picture of the derivative of color change. Where it's white, there's a lot of change, so that's over this moving car.
This is like the secondary.
That's effectively, right. And it's not just spatial, right? Okay, usually it's going to be, of course, cause that temporal change. On the right, the way we do adaptive gain control is by trying to figure out if things are changing more rapidly across space or across time. So on the right, we're showing the first pixel visualization of color gradients, and the green and yellow represent spatial change, the blue represents temporal change, and again, that's focused over the car. In this case, we're seeing that most of the color change is across space, but things are fairly static.
And then apparently your switch is off.
Oh, okay. So things are fairly static. I'm sorry. So we would have a large number of tiles. So I'll hand off to Dave now to talk about Reconstruction.
Let me jump in for 4 slides to talk about the Reconstructor, since that's the part that we've been working on. So Ben and his student built a sampler that's responding to change. It's sending us the stream of samples. The deep buffer is sort of our intermediary. It's a convenient way of storing samples, and we use a pretty simple regular structure where we store some number of samples within every pixel, and we sort of, newest one comes in, the last one falls out. So we've got this deep buffer which stores our sample in some volume of space and time, and now we need to generate images to actually show the user, what all the stream of samples represents. And so this is just like traditional reconstruction. You would do some form of filtering, right? You would, at every pixel, you would take the center of the pixel and you'd gather nearby samples and do some sort of weighted average where the weights are determined by a filter kernel. That's exactly what we're doing here, except that now, because we have to deal with this third dimension of depth, of time rather, our filter kernel has to be 3-dimensional instead of 2-dimensional. So we're filtering in both space and in time. We've got some decay, samples have some decaying amount of importance over time. But on the other hand, it's not sufficient just to say that old samples are all, a sample that's a millisecond old is always half as important as a sample that's brand new. You need the importance of samples to change, the importance of old samples to change depending on what's going on in the stream as a whole, what's going on in that part of the image. So how do we shape this filter? How do we size the filter? What's the total volume of the filter if you were to integrate the sort of the filter over some volume? In our case, the total volume is determined by the local sampling density. So if you have a region in the image that's getting sampled very fine, that's being sampled very finely, then that's going to affect the volume of the filter. The sample widths, the sample gradients are what determine the shape. So the idea here is that, as you saw on the right, you've got, this region is blue. It's blue because there's a lot of change happening in these regions of the image, and so things are changing. Old samples are not trustworthy. New samples are trustworthy. So we should use new samples. On the other hand, in these regions over here where there's no blue at all, things have not changed for many frames. The image is basically static there, and so we should be using old samples. They're useful. So we need to change the width, the width of the temporal width of our filter. And similarly, where you're near edges, which are the green and red lines here, you need to change the spatial width of the filter to try to not gather samples across edges. I'm sorry. So basically, two things should happen when you do reconstruction on these sample streams. When the scene is more or less static, or in places where it's static, you'd like to use old samples. And the more old samples you have, the better. It's going to, at some point, you're just going to start to use these samples to sharpen or even anti-alias your imagery. So what this is saying from the point of view of the filter is that the filter is temporally wide, right? It's very deep. Your old samples are almost as important as new samples. On the other hand, where things are changing a lot, then new samples are useful and old samples are stale. So you really want to de-emphasize the old samples and emphasize the new samples, even if the result is blurring, even if the result is that you're going to have a blurry but up-to-date image, as opposed to an image that's sort of speckly, because some of the pixels happen to be close to very new samples and some of them are close to stale samples. So what this is saying is that the temporal filter should be narrow and the spatial width should dominate. So we map spatial. So we map all of this to the gradient. So where things are changing quickly in time, you have a narrow temporal width. This is what that looks like. There's two segments from a scene. This is all from the BART benchmark, by the way, which is this benchmark by Thomas Muller and somebody else. It's basically a kitchen scene. So the viewpoint flies around the kitchen, and there's a little toy car that moves around. And here's two different segments in that scene. So here on the left, the viewpoint is near the end of the scene. The viewpoint has come to rest. It stopped moving and it stood still for half a second or something. And on the right, we're in the middle of a fairly high motion. We've been sitting still looking at this kitchen counter, and all of a sudden we started rotating our head to a new position. And so on top, we're using a temporally narrow, spatially wide filter. So we're counting new samples a lot and old samples not very much. And you see that this leads to more over blurring in the case of the static scene. But when things are changing rapidly, then you get at least something that represents the current viewpoint. This is blurry but up to date, which is what we want. Down here on the lower left, this is the static scene now that the camera has actually stopped and nothing is really changing very much. So those old samples should be used, and indeed they are. We use a temporally wide, spatially narrow filter. On the other hand, if you were to use that filter for the region of the scene where things are the region of the video where things are very dynamic, where the user is actually moving around, then you get these terrible kind of ghosting artifacts. You see here kind of the line of the countertop where it was, and we just started rotating our head, and this is where it really ought to be. And so this is just sort of illustrating that you're going to need to use different filters at different points in the segment and across the scene. You can have, like in that toy car example, everything's still except for this one car, which is flying across the scene quickly. So you need to sort of adjust within as well within a frame, within a single image that you're generating. I won't get too many of the details of this, except to say that, this reconstruction process, to be done right, it really needs some sort of support in hardware. It's pretty expensive to do this sort of gathering in the CPU. And so we're working on GPU implementations. How do you map this to current graphics hardware? My gut feeling is that it's basically not plausible in sort of NV30 class DirectX 9 hardware. Looking forward, future hardware, I think it starts to get more possible. Ideally, the Reconstructor would be the display, and you would send not images to your display, but samples to your display. And the display would be the thing which is integrating these samples and doing some sort of reconstruction process. And so, whether that happens in a video card that's attached to a display, or whether that's literally somehow part of, more intrinsically part of the display hardware is something I'm kind of curious about, and we'll return to that at the very end of the talk. In the meantime, everything we do is a simulation. We have a fast renderer, which is the OpenRT. That's the renderer by the Saarbrücken guys who use PC clusters. We have a fast ray tracer, but we only get like 50,000 samples per second out of it. We get a lot more rays per second than that, but we're casting shadow rays and reflection rays and so on. We're just trying to generate sampling imagery. So that's not quite fast enough for what we want to do for interactive scenes. So we simulate 100K, 1 million, 1 million sample per second sort of interactive streams. We fly around, record the path, and go back and say what stream of samples would we get if we had a sampler going at 1 million samples per second. And the simulation that we do of the reconstruction is entirely on the CPU at this point, and not very efficient at that. So maybe it takes us half a second to a second to generate each image. But that's life in simulation land. So that's the reconstruction part of this problem. And now Ben will tell you about how we sort of evaluate our results, and I'll sort of wrap up with our thoughts for the future.
So when we did the interruptible rendering work, one of the questions we had to address was, how do you know how well you're doing? The way we solved that problem was to compare our imagery to a hypothetical renderer that could render with zero delay all the detail available. So instant, basically. So of course that doesn't exist, but we can certainly simulate that and then compare to that simulated renderer. We call that the gold standard technique. What we do is compare at about, we usually compare at 60 hertz. We have to carefully account for things like how long it takes to render stuff, double buffering, and those sorts of issues. When we do this, what we're getting is, again, not just the spatial differences in the two images, but we're also getting effects of delay, because the instant render, is completely up to date, this ideal renderer, but our renderer and others are not quite so up to date, and so we'll capture those effects. We also, qualitatively at least, looked at something we call an oracle-based reconstructor. That is, given that we're generating a certain stream of samples, if we could sort of magically figure out which samples were good and which samples were bad, how well could we do? And the way we found those good samples was by comparing them and making sure they're close enough to this ideal renderer before we did a reconstruction. So let's look at some of those pictures. On the upper left, that's a regular frameless renderer, and you can see what's going on here, and we'll see this in a second, is that the car is moving across the scene and then approaching the viewer. And you can see that at this sampling rate, which is roughly, all of these have the same sampling rate, by the way, it's roughly 20 times too slow to make a complete 60 hertz frame. It's really, the renderer is really having trouble capturing and defining that moving car. On the upper right is a fairly recent reconstruction from our adaptive sampling. And it's a little blurry, and there's a little bit of some out-of-date stuff behind the car, but it's certainly better. On the lower left is the oracle image, a little bit better defined. And on the lower right, the ideal image.
It's really hard to evaluate these without seeing the animation.
Yes. So here are the animations. Just click on it. So we'll be looking at 4 different image streams here, or videos, if you will. 3 of them represent fairly traditional solutions. One says we'll just do 60 hertz, whatever the resolution. That's the upper left. The one on the upper right says we'll do the resolution, whatever the hertz. The one on the lower left is frameless rendering. And the one on the lower right is an ideal rendering. So these are the existing solutions.
The one on the lower right is the speed of light, right?
Yeah.
You can't achieve that rendering.
That's completely simulated. So now we're going to look at a few variations on our temporally adaptive frameless renderer. In this case, what we're tweaking are whether or not the tiling is adaptive, whether or not we have this gain control, and then also how big is the response to the derivative of color change or edges in space or time. So 3 variations on those themes, and then the ideal rendering on the lower right. Our opinion is that the upper right looks best of the 3, for this particular scene anyway. And now we're going to compare the best of those to a couple of more traditional approach or previously existing approaches.
Pay attention to the traditional frameless and look at how little data the system is actually getting. I mean, this car moves very fast towards the end, especially. There's very few samples that we have to use. Don't get thrown off by that sort of speed of light image on the right, which is what we couldn't possibly render. That's
a good point.
Very little data.
So when you do this reconstruction, do you have access to samples that are from other places that you can predict to move someplace else, or is it only in the actual tile? It has to be within that tile in order to be used.
In these renderings, we weren't moving samples around. We were just rendering them and leaving them there.
But it's very much something we're going to do.
Yes. So here's another video looking directly at.
I don't think it took.
Huh?
Clicking.
I didn't click yet.
Oh, okay.
Looking directly at sort of the head-to-head comparison, and in this case, it's using an interactive animation. So instead of a fairly static scene, we have a scene that alternates sort of overall between static and dynamic. Unfortunately, there's a little bit of compression artifacts that crop up here, but still illustrative. So the lower left is the adaptive frameless approach. The upper right is low resolution. The upper left is just regular frameless rendering. So we can also do some numeric comparisons. In this case, we're just using those same image sequences. This one is the car scene. We're just comparing imagery at 60 hertz. They're not really frames. They're whatever was on the screen at 60 hertz, and doing root mean squared differences. And you can see that in general, the low resolution stuff is worse. The regular frameless renderer does fairly well until the car turns and approaches the viewer. And then the differences increase between the thick lines, which is the adaptive stuff, and the regular frameless stuff, the thin line, and then the gray line. And here's the interactive recording you looked at. Essentially what's going on here is that the adaptive renderer is functioning more or less like a minimum between the regular frameless renderer and the low-resolution framed renderer, sort of getting the best of both worlds here. These peaks represent periods of viewpoint change, and the valleys between them are where the viewpoint goes static. You can see, for example, how the low-resolution renderer never really never really generates a nice fine image, even when things go still, whereas the frameless renderer has trouble when things go dynamic. And then here's an even more dynamic comparison. We didn't show you this video, but essentially what's going on here is that the viewpoint is always in motion. And once again, I mean, the error in general is higher, but overall, the adaptive renderer is definitely winning out. If we, just by way of example, improve the sampling rate for all the renderers so that it was about 50% what you would need to do 60 hertz frames, we get a clearer win. One interesting thing to notice here is we threw in for illustration the high resolution renderer, and here you can see the effects of double buffering in the sawtooth error pattern. As the frame is displayed, error is increasing while the rest of the world is moving on. And then a new frame generates, error gets reduced. So now, if there are no questions, hand off to Dave for some discussion.
Okay. Hopefully you're not dizzy yet. So, so we just have this sort of laundry list of things we want to bring up because this is very much work in progress. We think it's pretty exciting is where it could go. There's still a number of things to do. Of course, one thing we want to do is get this working in real time, and that clearly means implementing it on hardware. At least the reconstruction needs to be done in hardware. And so can we do it on existing GPUs, NV40 class GPUs? Can we do it in the future on whatever's coming down the pike? We think so. We also are very interested in extending these ideas to sort of true global illumination. Right now, our samples are like, we take sort of a single sample in the image plane. But if you were really going to capture global illumination effects, you'd like to be able to do techniques like path tracing, where you're going to have a whole bunch of samples, and those samples are going to be quite different. Some of them will be in shadow, some of them will be occluded. And so you have to be able to untangle a difference because you took a different path through a given spot on the screen from differences because something has changed in the scene. And so we think that this is doable. We don't have it well worked out yet, but it definitely will involve sample reprojection, which is the next step. And I'll just briefly mention that, on the other hand, photon mapping, which is a technique used in global illumination to basically to capture certain indirect illumination effects and caustics and so on. Photon mapping actually should map very clean. You can imagine a photon map which was itself framelessly updated over in a temporally sensitive way. So you'd shoot more photons to regions that are changing. The importance of photons would change in time depending on how much things are changing in that spot. We haven't done it. We're working on it. We think that's a really promising place to sort of take this approach because people are starting to think about photon mapping in interactive settings, and everybody who's doing this is realizing, oh, we really need our photons to last more than one frame because we don't have time to shoot enough photons in a single frame. Sample reprojection. This is just this idea that once you've shot it, once you've gathered some information about you shot a ray, it hit something, you got a color. Don't just throw that information around. Keep track of how it's moving. And there's several ways you can do this that people have played around with. If the only thing that's changing in the viewpoint is if the only thing that's changing is the viewpoint, then all you have to do is keep track of its depth, and that's enough information to do a reprojection as the viewpoint moves to new locations. And if it's diffuse, and so things get stale faster if they're highly specular, for example, that's something that could be incorporated into this. Also, if the objects themselves are moving, maybe what you want to do is actually, ray trace velocities as well as location. Keep track of the object velocity that you hit in image space or in object space. We haven't done it. We're excited to do it. That's sort of ongoing work. Edge-sensitive reconstruction. Just to mention here. So there's this kind of key insight in Reconstruction that most of what you're trying to do in Reconstruction is not include the wrong samples. Samples that are on the wrong side of a spatial edge are going to lead to blurring of edges. Samples that are on the wrong side of a temporal edge are going to lead to sort of disocclusion, occlusion artifacts, disocclusion artifacts, things leaking through. So an example of work that's been done on this problem is Kavita Bala's work and coworkers' work with where they actually pick samples with respect to edges. So here, on the left, you've got a whole bunch of samples generated by a nice path tracer, but it's a fairly coarse sampling. This is not nearly enough samples to fill out the image. But what you see is they've also used silhouette finding techniques and some techniques from sort of the old discontinuity meshing work to find places where there are going to be edges, shadows, penumbra, umbra, and silhouettes in the image. And when they generate their final image from this coarse sampling, they don't respect samples which are on the wrong side of an edge. So they sort of rasterize the edges as well as the samples into their buffer. So this is this is an example using a priori knowledge, geometric information about the scene in this case, to tell you which samples are right and which samples are wrong from a spatial point of view. We might be able to do something similar from a temporal point of view. We might be able to figure out kind of a priori, hey, there's been some motion and these samples can just be thrown out. I think that might be kind of hard. I'd rather do something that's more purely image-based. And what you're really talking about there is robust estimation of samples. And so bilinear filtering, for example, is one technique that's been proposed for this. Jack Tumblin, who works with Ben, has this trilateral filtering paper a year or two ago that they employed in tone mapping, and we think we could use some of those same ideas in the reconstruction process. Sample reprojection, it's a big part of MPEG compression. you know, we'd like to point out that we think that, I mean, at least according to our current metrics, which, you know, are arguably not perfect, they're definitely not perfect, but we're getting improvement already, and we're not even accounting for sample motion. As you see, I mean, that's a key part of video compression, for example, is keeping track of how things, of optical flow and how things are moving. And so that we just think that's important. And we also think that if our samples lasted longer because they were being reprojected, then that would probably improve just the whole control theoretic properties of all the control theoretic properties of the system. The feedback and response should improve. And the renderer, this will also just naturally let the renderer, help the renderer focus on occlusion events, which is the real problem with frameless rendering, right, is the front edge or the back edge of a moving object. You can imagine if you're doing sample reprojection, and so this moving object, all these samples from the front edge of this object now get piled onto what was the background because they got reprojected there. That's just going to increase the gradient, the apparent temporal gradient in that region, and you're going, and that's just another signal to your sampler that it needs to focus sampling resources there. And disocclusions are slightly harder, but again, we think the same basic idea can happen. So sample reprojection is clearly an important ingredient to include in this. Anybody who's worked on fast ray tracing is going to say, but you're giving up a huge ingredient to fast ray tracing, which is coherence, right? I mean, part of what makes these ray tracers fast is the fact that we ray trace little bundles of rays all at the same time so that the cache is warm. When we trace right through one pixel, the next pixel is probably going to hit the same things. And so it's very important that your cache be warm if you want full performance out of your renderer. And so we are implicitly in frameless rendering, we're giving up some spatial coherence, right? We sample here and then here and then here and then here, and our cache is continuously being thrashed. So that's a big win. That's a big hit that we're taking. Now we can partially ameliorate this by the fact that we have this sort of tiled structures. You can imagine that if we didn't sample like one sample per tile, but many samples per tile before moving on to the next tile, that would help ameliorate this problem. And it's also worth pointing out that in principle, we're gaining a coherence. We're gaining temporal coherence out of this ray tracer because we are not regenerating rays every frame in these regions of the scene that aren't changing. We're not having to shoot all those rays again. And so we have fewer overall samples because we don't need to resample the entire image every frame. You know, is temporal coherence worth more than spatial? Well, I mean, time will tell. That's kind of the key question. It's the key question going on here. So we think so. We think that we're gaining a lot of temporal coherence and we're giving up a little bit of spatial coherence. But that's certainly a criticism that anybody who's done fast ray tracing is going to bring to this work. Finally, you know, fundamentally what we're doing with frameless rendering is kind of a mismatch with current display hardware, right? I mean, display hardware today is all built around frames. It's this idea of images, images as a raster grid of samples is baked really deeply into display hardware. This idea of frames as, you know, component images of an animation is a really deep idea. And so what we do now is kind of expensive. Unfortunately, we have this sort of resource-heavy reconstruction step where we've got a stream of samples coming in, and then 60 times a second we generate a frame from our frameless rendering. So we'd like to investigate sort of a different frameworks for doing that. Maybe we can build these frames incrementally, just sort of as each sample comes in, lay it down onto sort of an existing image, and in some way. But like I said, I'm kind of curious to think about, you know, in the long term, sort of more exotic, futuristic display technologies, whether or not you actually need frames in the traditional sense that are baked directly into the display. I think that this is really interesting with sort of, you know, e-ink and organic LED and these sort of more exotic displays out there. And you can think of this too. Think about a gigapixel display, right? Think about this entire wall being addressable at, you know, at less than, you know, at sub-millimeter resolution, being able to turn that on. How are you going to drive that display? And does it really make sense to drive every pixel on that display continuously at 60 hertz or 100 hertz or whatever it is you're doing? Or does it make sense to be able to sort of direct rendering resources where they're most needed, where things are changing, potentially where the user is looking? That's another, you know, factor. You know, we're not going there, but that's something else you could think about. So these very, very large displays with very fine addressable resolution. I think that's a really interesting aspect of this work. I think our technique should be well suited to that kind of hardware. You know, I like to think of Reconstruction as an integral part of the display, and I sort of imagine this display, which is fundamentally sort of a systolic array of pixels, and I throw samples like darts at this array, and the samples get there and they kind of diffuse outwards. If you have lots of samples that are all recent, they're going to, you know, the area of effect of each sample is going to be quite limited. Whereas if I have only a few samples, you know, they can spread out much more. And you can imagine that maybe there's some way to cast this reconstruction as a diffusion across pixels. And now the input, you know, what comes over the cable that you plug into the display is not a series of images. It's a stream of samples. You know, so that's clearly a little more out there, but I think it's kind of exciting. And one interesting thing about this is that when parallel graphics becomes asynchronous, then that's a good thing. I would argue. You know, you've got this sort of classic taxonomy of parallel graphics. You know, you've got sort first, sort middle, sort last, and all of these have this sort of common constraint that are trying to generate an image, a single image, and then they're all going to move on and generate the next image. And if you don't have that constraint, or even view it as if it's been taken care of by the display, if you sort of don't have to think about that constraint, then you sort of break this frame and you break this sort of underlying assumption. That's one of the binding constraints in parallel graphics. So just to wrap up, we think this technique has advantages. It's clearly a work in progress. There's plenty of improvement to be done, but we think there's some really intrinsic advantages. Higher accuracy because you're focusing your sampling resources where they need to be. So if things are changing rapidly, you're getting a blurry but very up-to-date image. If things are not changing, you're focusing just on the regions that are changing. Because it's this self-monitoring closed-loop feedback system, you've got high portability, so if the rendering load increases or you change rendering platforms, that's okay. You have sort of graceful degradation. And there's just a lot of trends out there the things that this implies are trends out there that I think are good. This notion of focusing rendering in regions of change is important. I think irregular sampling in hardware is something that people are starting to play with. You know, Bill Mark has some work at Texas, you know, trying to do irregular sampling. Other people are proposing offset buffers is the name of a TVCG paper. There was a paper at EGSR this year where they used irregular shadow maps. That's, you know, the idea of doing irregular sampling is not necessarily foreign, and it's worth mentioning that some of these are rasterization-based techniques. So maybe these ideas can be mapped, in fact, to a rasterization, not a ray tracing framework. Yeah, I think the fact that sort of the intrinsic load balancing that you might get from sort of asynchronous parallel graphics is a promising implication or trend. And, you know, we think it's interesting when you start talking about sort of hyper-resolution displays, these gigapixel display walls. You know, kind of an exciting place to think about that. So I think that's it. That's our talk. So thanks for listening. So, any questions? Yeah.
I don't know if it just got lost in the hiding of the implementation, but I felt like there was a duplication of work when you're talking about the Reconstructor tries to figure out which samples are in that 3D data structure are important, but you already have that importance data from your feedback loop. You tried basically passing that along as a sort of metadata along with your map?
You want to answer that? I'll make the first minute. So that's a good question. From an implementation point of view, partially just because of physical location, he's in Chicago and I'm in Virginia, we actually made the decision kind of early to see how far we could get with very separate, where all the Reconstructor gets is a stream of samples. On the other hand, we've broken away from that a little bit. The Reconstructor does also get the tilings and uses, for example, the gradient information that's intrinsic in those tilings. So yeah, I think that if you were really to implement this, it depends on if you were trying to do remote graphics or something, maybe, you know, what the choices you would make. But yeah, clearly there is potential for some redundancy if you have both Reconstruct and sampler calculating gradients and so forth. Do you have anything to add?
Yeah, my only other thought is that, for example, like Bala, we might actually explicitly encode edges in the buffer, which we aren't doing now, right? But all of those.
If sample reprojection were to happen in the Reconstructor, that information would have to be fed back to the sampler at some point, right? You know, because you'd have regions of the screen getting empty because all the samples have left, and you need to tell the sampler that some way. So that would play into it. And that's a good question. There's sort of the possible architectures. There's a wide range of partial architectures you can throw on this.
You mentioned computing velocities in space. Did you work on that and rasterizing velocities very quickly?
Yes. I will remember it.
I can't think of them.
Bill Mark has a chapter in his thesis that talks about this. Bill Mark's thesis in North Carolina was an image-based rendering technique for remote rendering. So you'd have a high resolution, you have a server that was generating, very nice images with depth of disparity at every pixel, and you'd have some sort of local warping engine that was sort of your thin client that would warp between a couple of these images. And you can do that warp better if you have velocity. And so he talks about that. I forget whether he did it himself. I don't think he did, but I remember his thesis talks about people who have done it.
You can do it. It's not that hard. It's just camera motion, but if it's lighting change due to dynamic scenes, like some piece of glass is casting a caustic and you're changing the light by sticking your fingers and waving like this, computing the derivative in image space for that color change is going to be really difficult. Yeah, not just sampling it and taking the difference.
Yeah, I think you punt on that. I was thinking more just of actual motion. I agree. I think you punt on that and let the image itself be what tells you that there's change. But sort of first order, what surface is there at that pixel kind of information is useful.
Yeah, how is it moving in 3D or in 2D?
Yeah. But no, I agree with you. You don't want if you push that too far, it just gets insanely complicated. But object velocities, that information is there. It seems pretty easy.
Model transformation matrix with a derivative information somehow.
And this is predictive, remember. I mean, so if something goes in, if a sample is mispredicted and goes into slightly the wrong place, hopefully we've got enough other sampling that we catch, that sample gets kind of booted out. I mean, this is, or it looks like a mistake, and so the sampler sends lots of new samples in that region. I mean, the fact that this is this closed-loop system will solve a lot of your problems.
We hope.
As long as your sampling rate is high enough. I mean, by construction, our examples are extremely low sampling rates. A 20th of the samples that you would need. That's, and yet we do reasonably well. I mean, clearly, you can think of the other extreme of this, where we've got enough samples to touch every pixel every time we're going to display an image. I don't want to call it frame, but every time we're going to reconstruct an image, we've got at least one new sample at every pixel, but we're using this technique to focus anti-aliasing resources. You can think of this, or if you start thinking about path tracing, we're using this technique to see how many paths we trace. That kind of refinement is sort of the other end of this spectrum. You could apply these same sort of ideas to, perhaps.
We talked about occlusion and distribution artifacts. So if there are some samples which are occluded, which should not actually contribute to the image, is there a way of figuring that out? Whether a sample should contribute or not?
Well, we haven't done it yet, but at a first pass, and I always like to do the first pass first, what would happen, as Dave mentioned, would be that samples would get mixed up. Stuff in front would get mixed up with stuff in back. And the sampler gets curious about that, right? It sees that there's some kind of change happening there, and it begins sampling there more often. And as that happens, effectively what it's doing then is it's making the incorrect samples obsolete.
They have less weight, contribution.
Yeah, as they age, basically, I don't know if we mentioned this explicitly, but older samples count less, and eventually they drop out of the buffer. Yeah.
The implementation-wise, just because this is what maps well to GPUs, what our buffer actually is, the deep buffer actually is a stack of pixels, a stack of samples for every pixel. And so, the 10th arrives, or one arrives, the 4th falls out. That's not the only way you could implement it, but it maps well to graphics hardware, which is sort of what we were trying to do originally, was do this entirely on the GPU, and then we backed off a little bit. So let's do this in simulation first and see how good we can make it. So in fact, old samples will pretty quickly just kind of fall out the back. But even if you kept them around forever, the fact that the sampler is sending lots of new samples and the fact that there's a gradient there should prevent those old samples from contributing really quickly.
So, I really like your idea of thinking about interesting reconstruction that happens in the display. But to me, I'm thinking, what about this kind of reconstruction? If I just have a diffuse object that's got a texture map and I'm moving my viewpoints around, wouldn't it be a really nice compact operation to store a polygon mesh with a texture map and be able to reproject through any possible view? So that in the Reconstructor you end up sticking back all the graphic stuff as a model for what you can see. Maybe you simplify the shading models and stuff on it, but you guys have gone to the very lowest common denominator where you just have point samples in time and space, but does it make sense to go to higher order things that we sort of already do with computer graphics and use those as primitives in the Reconstruction?
I mean, that's, I mean, the sample reproject, simple sample, stop, hit the stop button. The simple sample reprojection, I like, it's simple enough that I'm kind of willing to go there. I agree, I think you start to lose the whole point of it. You know, the potential benefit of...
I think the point is that if it's photorealistic rendering, and the shading models you do for ray tracing are incredibly complicated, you know, just very compute intensive. But if you can figure out, like, a model that you can, like, sometimes in ray tracing, for example, you get these low frequency, like, penumbras, okay? If you knew that it was a penumbra, you could sample it very coarsely and use a very low frequency filter to get back a pretty good approximation. But you have to know that it's a penumbra and, like, sort of where roughly to sample it and stuff like that. So I can see, like, mixing kind of these simple models that we already do in computer graphics, but to do the lighting, you have some sort of predictive like approximation that's pretty accurate.
I think essentially what you're talking about is, I mean, maybe not do this thing as a full-blown renderer. This is the render, right? Like maybe it could be a supplement and doing.
Or the photon map, for example. That's yeah. The photon map is a place where there's a nice data structure, and if you just updated the photon map, which does basically indirect illumination, tends to be pretty robust to sampling error, or to sampling variance, I should say. Because it's capturing more or less mostly low frequency effects, right? That's you get indirect illumination. So I think the photon map is one example of where these ideas might map really pretty naturally into global illumination kind of setting.
I guess the other thing I'm saying is it's dangerous to make the lowest common denominator be really, really stupid because
we have
the whole
more.
trend now is to make the graphics hardware smarter and do more things on the fly rather than making it really stupid and just do a very simple reconstruction and having the front end compute lots and lots of samples so it can do a decent job with its stupid reconstruction. To make the reconstruction smarter, maybe. I mean, doesn't that seem like the trend that we have, that in the graphics side we're absorbing sort of more of the interesting shading functionality at the sort of very bottom end?
It's also a trend, I mean, I'm thinking about geometry images and user stuff, and there's also a trend towards simple and regular, but very, very fast.
Well, but your thing isn't that simple and regular. It's less, I mean, you're going away from the simplicity and regularity when you go to tiles and time and space that are variable and so on.
It's pretty important to separate the sampler and the reconstructor in this. I mean, the reconstructor is, I think, the thing that can be made very simple and regular. I hope that it can be made very simple and regular. That's why I have this idea of sort of diffusion-based reconstruction.
But then, if you did diffusion-based reconstruction, you'd want to code like sort of what are the edges on the regions that you're going to solve as a single partial differential equation, right? So there'd be some sort of region coding thing. Because the whole point, you don't want to solve the diffusion equation across the edges where that diffusion equation is the relevant one, right?
You're talking about this a priori knowledge. Sort of.
Well, we have some of that because
we do have some of it. Yeah. Yeah, exactly.
Thank you.